So in this lecture, we're going to review some of the material that we've already seen about Laplace transforms so that we're ready to apply them to solve systems of differential equations in the next two lectures. So this is going to be something of a revision class, reviewing Laplace transforms, inverse Laplace transforms, the first and second shifting theorems, and the Heaviside function. So let's get started. So we're going to begin by reviewing some techniques for sketching functions involving the Heaviside function. Let's start with example 1. We're asked to sketch each of the following functions. And what I'm going to do here is write each of these functions, which are expressed in terms of a Heaviside function. I'm going to write each of these as a piecewise continuous function. And I'm going to do that by splitting the function up into the various parts of the domain of t. So let's start with part A. We're asked to sketch the function f of t is equal to u of t minus 5 minus 1, where u of t minus 5 is our Heaviside function. Let's just remind ourselves what the Heaviside definition of the Heaviside function is. So we have u of t minus c is a function which is 0 when t is less than c, strictly less, or it's 1 when t is greater than or equals to c. And we have to pay close attention here again to the less than and the greater than or equals to when we're sketching our function, because that's going to tell us which points are enclosed or concluded and which points are not included at a particular value. So let's now use this definition to split up our values of t into two possible intervals. We've got t is less than 5. You can see that the Heaviside function here is going to change things up at the value t is equal to 5. So we've got t is less than 5. And we've got t is greater than or equals to 5. And again, note here that the less than and the greater than or equals to matches our definition that we are using in this course for the Heaviside function. So for values of t less than 5, we know that this Heaviside is going to be 0, which means we have 0 minus 1, we're going to have a value of minus 1. While for values of t greater than or equals to 5, our Heaviside will be 1, we'll have 1 minus 1, we have 0. So now we're ready to sketch this thing. Let's draw the t-axis. And again, as usual, I'm going to be taking t to be a positive number, so I don't need to bother about values of t less than 0. So let's just save my little axis here for future use. Okay, now we're ready to sketch. So what this function is going to look like is something that changes at t is equal to 5. So let's put 5 right here. For values of t less than 5, this function is going to have the value minus 1. And for values of t greater than 5, it's going to have the value 0. And we can put a little arrow there to indicate that that value 0 is continuing off for infinity. Now again, as always, we need to say what's happening at the discontinuity. And we can see from our definition of our function here, this piecewise continuous definition, that the value t less than 5 is not included. So approaching from the left-hand side, this is not included. And approaching from the right-hand side is included. Should also probably fill in the value at t is equal to 0, because we're looking at values of t greater than or equal to 0. So that's what our function looks like, and you notice that it looks very much like a Heaviside function, except that it's been shifted down by 1, which is exactly what this minus 1 is doing. Let's take a look at the next bit. So the function we're asked to sketch is f of t is equal to 1 over t u of t minus 2. And once again, the Heaviside is there hinting at what we need to split up our values of t into. We're going to have t less than 2 and t greater than or equals to 2. So for t less than 2, this thing is going to be equal to 0. So I'll have 0 here. And for t greater than or equals to 2, I'm going to have 1 over t times 1. I'll have 1 over t. So this is the function 1 over t switching on at t is equal to 2. One thing to note here, of course, is that 1 over t goes a bit bananas when t is equal to 0, but we don't worry about that here because the Heaviside function is taking care of that value at t is equal to 0. It's going to be equal to 0 there because this function hasn't been switched on yet. So let's sketch what this thing looks like. And we're going to see that things are going to change at t is equal to 2. So let's put that right about there. And it's going to be equals to 0 until that point. And then it's going to increase like, it's going to decrease like 1 over t. So I'm going to draw that like something like that. So this is the function 1 over t. And it takes the value at that crossover point, at that discontinuity. The value of my function is a half, 1 over 2. And we're going to include this point and not include that point. Again, that's coming from our definition here. We're not including the point less than 2 for 0, and we are including the point greater than or equals to 2 for 1 over t. Let's take a look at the next one. You can see that this function here was a bit like 1 over t, except it was chopped off. Of course, we call that a cut. So we could almost imagine that we had taken 1 over t and chopped off all those values for t less than 2. Let's take a look now at an example of a shift plus a cut. So in the next function that we're looking at, we're looking at c. F of t is equal to t minus 1 cubed, u of t minus 1. So again, that Heaviside is hinting to us, it's telling us how to divide up our values of t. So it's saying we should look at t less than 1 and t greater than or equals to 1. That Heaviside is turning things on or switching things on at t is equal to 1. So that's where we need to divide up our values of t. So for t less than 1, this Heaviside will be 0, so this whole thing is switched off. And for t greater than or equals to 1, the Heaviside is 1, and so it switches on the function t minus 1 cubed. And you notice that this t minus 1 cubed is basically a shifted version of t cubed. So it's going to look like t cubed, except it's going to be moved over right where that Heaviside is switching it on. This is a switch plus a cut. So let's sketch this, and again we'll use our pasted axis. There we go, lovely. So we need to see what happens at t is equal to 1. So let's draw in that point. Here's t is equal to 1. We know that this thing is equal to 0 up until that point. We're going to include the point at t is equal to 0. So at t is equal to 1, we now switch on the function t minus 1 cubed, which looks like t cubed, except it's been shifted over by 1. So that's going to grow like that. So we're going to write that as t minus 1 all cubed. And you can see that there's actually no discontinuity with a shift plus a cut. Those 2 points actually overlap one another. And you can check that by looking again at our piecewise discontinuous value. When I stick in t is equal to 1 here, I'm going to get 1 minus 1 cubed. I'm going to get 0. So these 2 pieces of my function actually connect up with one another. Now, we have a fourth example here, so let's take a look at that. We're going to need an extra page, so let's see if I can figure out how to do that. Beautiful. So here's our function that we need to sketch. It's f of t is equal to e to the power of t, u of t minus 5, minus u of t minus 7. So we actually recognize this combination of Heavisides as a switch on, switch off. It's going to switch on this function at t is equal to 5, and then it's going to switch it off again at t is equal to 7. However, I'm not going to just write down the answer just yet. I'm going to again use my trick of dividing this up into piecewise continuous functions. I'm going to do that by identifying the different ranges of values or intervals in t, and those are going to be divided up by where those switchings are happening. So I've got a switch at 5, I've got a switch at 7. So that's going to give me 3 different ranges of values of t. I've got t is less than 5, I've got 5 is less than or equals to t is less than 7, and I've got t is greater than or equals to 7. Now you notice here that I actually was a little bit careful about where I placed my less than and my greater than or equals to, or my less than or equals to. And the reason I did that was to match that definition of the Heaviside. So the Heaviside doesn't include the point on the left, it does include the point on the right. So you can think about this t5 is less than or equals to t is kind of like t is greater than or equals to 5. So this is consistent with the definition of the Heaviside that we used at the beginning of this lecture. So now we're going to have to look at what happens to this function in these 3 different ranges of values or intervals. We know that when t is less than 5, then this is going to be 0 and this is going to be 0. These are 2 levers and neither lever has been switched on yet. So this is going to be 0 for t is less than 5. Between t is 5 and t is 7, this one is going to switch on and this one is not yet switched on, so I'm going to get a e to the power of t times 1. So that'll be e to the power of t. And lastly, I've got t is greater than or equals to 7. So that means that this has been switched on and this has been switched on as well. So these two actually cancel each other out and they give me 0. So I'm going to get 0 again. So we can see that this expression confirms our intuition of this function as a switch on plus a switch off. Our function was 0 to start off with, then it gets turned on, it becomes an e to the power of t, and then it's 0 again, it's switched off. So again, we're thinking about this combination of Heavisides as a switch on, switch off. So let's sketch this. So I'm going to see that things are going to change at t is equal to 5 and t is equal to 7. Come on. There we go. T is equal to 5 and t is equal to 7. So let's stick those in. Everything's 0 before 5. And everything's 0 afterwards as well. All we have to worry about is what's happening in between. So this is going to be the exponential function. It's not been shifted or anything, so it's going to start off at some value here, and it's going to be growing up to here. Those values are going to correspond to e to the power of t, right? So this is e to the t. So when t is equal to 5, that is the left-handmost point, it's going to take the value e to the power of 5. And on the right-handmost point at t is equal to 7, this thing will take the value e to the power of 7. Now we need to figure out what's happening at the discontinuities, and that's going to be given to us by these definitions here. So we're not including this point. We are including this point, we're including this point, and we're not including this point. And you can see that from the definition of the Heaviside function, we tend to include the point for functions coming in from the right-hand side, but we don't include the point for functions coming in from the left-hand side. So thinking about it, we're coming in from the left-hand side, we don't include that point, we jump up and we include the point going off to the right. We don't include it on the left-hand side, and then we include the point as we go off to the right. Okay, so that's a simple example, a series of simple examples looking at calculate or sketching the functions involving Heavisides using their definitions in terms of piecewise continuous functions. And it's important to go through those steps and to be consistent in our use of less than or equals to, greater than or equals to, and how we sketch which values are being included or not included at the discontinuities. And the rule again is that for this to be a well-defined function, then we can only have one value for the function for each value of t. Let's take a look at the next example. Here we have calculating a Laplace transform of a particular function. And we're going to do this using the first shifting theorem. So we always do this whenever we see that a function of t has an e to the something t in front of it. So we've seen that the first shifting theorem tells us that whenever I multiply by an exponential in t world, that corresponds to a shift in s world. But we're going to see that we have to be a little bit more careful than that. So let's take a look at what the Laplace transform of this thing is going to be. So we have e to the 4t, t to the power of 5. And we can see that this gives us, comparing it with our definition of the our definition of the first shifting theorem, that we can read off that a is equal to -4 and f of t will be t to the power of 5. So what I need to do now is use this f of t to figure out what big F of s is. So big F of s is going to be the Laplace transform of my function f of t, which again is the function without that exponential in front. So that's going to be the Laplace transform of t to the power of 5. That's one of our tabled Laplace transforms. It's going to be s, or m factorial, so m here is equal to 5, so it'll be 5 factorial over s to the power of 5 plus 1. So that's going to be 5 factorial is 120. That's 1 times 2 times 3 times 4 times 5, all over s to the power of 6. Okay, we're not finished yet, however. Because we have that exponential here multiplying our t to the 5, when we move into s world, when we look at our Laplace transform of this function, we're actually going to have to take this function of s and shift it by a. So this implies that the Laplace transform of the exponential times t to the 5 is going to be the shifted function fs plus a, so a was -4. So everywhere I see s in my expression above, I'm going to replace it with s minus 4. And there we have it. We applied the first shifting theorem to calculate the Laplace transform of an exponential with respect to t multiplied by a function of t. Now we're going to use the same first shifting theorem, but in reverse. We're going to use it to calculate an inverse Laplace transform. And so we know that we need to do this because when we look at the function of s that we're trying to deal with, it's clear that everywhere in this function, s appears in the combination s minus 12. In other words, this is clearly a shifted function of s, and I can see that the shift is going to be a is equal to -12. So let's write down what the shifted function is. And then it's easy to write down what the unshifted function is. That is, the function without a shift. Now I'm ready to calculate what f of t is. F of t will be the inverse Laplace transform of the unshifted function. No shift. So it's the inverse Laplace transform of s over s squared plus 1. Again, that's one of our tabled Laplace transforms, and that's going to be given by cosine of 1 times t. We're not finished yet. Of course, the inverse Laplace transform of the shifted function from the first shifting theorem is going to be an exponential e to the at, so a here was minus 12, so I've got minus times minus 12. So again, a is equal to minus 12 here. So e to the minus at times the function of t, so that was cosine of t. So that gives me e to the 12t cosine of t. Okay, let's take a look at example 4. So here we have a function that we're given again as a piecewise continuous function. We're going to sketch it, we're going to express it in terms of Heavisides, and then we're going to find its Laplace transform. So, first things first, let's sketch it. So that's relatively straightforward to do here. Let's look at the definition. Oops. This thing is going to be equals to 9 between the values t is equal to 3 and t is equal to 4, and it's going to be 7 outside of those values. So between t is equal to 3 and t is equal to 4, it takes the value 9. And outside of those, it takes the value 7. So we're including that point. This is the value 7, this is the value 9. And we need to decide what happens at the end, or the discontinuities. And then again, that's going to be given to us by the function itself. So we notice that we're including the points at t is equal to 3 and t is equal to 4 with the value 9, and we're not including them at the value 7. So we're not including this point, and we're not including this point. We are including this point, we are including this point. Now we need to express this in terms of Heavisides, and we saw that this looks a lot like the switch on, switch off function, except for two things. The first is non-trivial and the second is trivial. Let's start off with the non-trivial difference. We remember that the switch on, switch off would go from 0 up to some function, and then it would go back to 0 again. But this is going from a value 7 up to a value 9 and then back down to 7 again. But that's easy enough to fix. All we're going to do is just add a background value of 7. So let's take a look at that. So the corresponding switch on, switch off function would be u of t minus 3, switch on at 3, and switch off at 4. So that's the switch on, switch off. And the way we're going to code this up is we're going to write this as a background value of 7 plus a little extra bit, right? So we have a switch on, switch off with a magnitude of 2, and it's on top of the background value of 7. So we're traveling along, we're happy at 7, and then when we hit 3 we jump up by 2, we travel along, and then we switch off that extra 2 to get back to 7 again. Now, there was another difference between this and the actual switch on, switch off function, and that had to do with what happened at the discontinuities. In fact, if you remember, in the last example, we looked at the switch on, switch off function, and we didn't include the left-hand point, that is coming from the left-hand side, and we did include the right-hand point, that is coming with our function along the right-hand side. But notice here that we don't do that on this discontinuity at t is equal to 4. As we come in from the left-hand side, the definition of our function is actually that we include this point, but don't include this point. So that's actually slightly different from the way that we have defined the switch on, switch off function in terms of our Heavisides. But that's actually not too much of a worry, because ultimately what we're doing here is calculating Laplace transforms, which means we're going to calculate integrals. And integrals don't really care about what happens at discontinuities. They don't care whether the point is here or whether the point is here. So there is a difference between the function that I've written down here and what's actually sketched, but it's a difference that doesn't actually make any difference in the end. It doesn't matter. So we're going to sort of smooth over that difference, and we're going to use this expression here as the definition of our function in terms of Heavisides. And now we're ready to calculate what the Laplace transform of this. We're going to define big F of s as the Laplace transform of f of t. Again, we're going to take advantage of the fact that the Laplace transform is a linear operator, which means that I can take this function of t and split it up into its constituent parts. So I have Laplace transform of u, Laplace transform of u times, Laplace transform of 7, Laplace transform of 2, u of t minus 3, minus Laplace transform of 2, u of t minus 7. And now we're going to make use of the Laplace transform of a constant, which is going to be 7 over s. The Laplace transform of 1 is just 1 over s. And we have the definition of the Laplace transform of the Heaviside. So let's take a quick look at that. It should be written right here. So this is the Laplace transform of our Heaviside. So we can see that we're going to write this as e to the minus cs over s. So it's going to be e to the minus 3s over s and e to the minus 4s over s. That shouldn't be a 7, that should be a 4. Okay, so we have 2 times e to the minus 3s over s. Comparing these two expressions here, we have this is clearly c is equal to 3, and this is c is equal to 4. So it's going to be minus e to the minus 4s over s. So there's our expression for our Laplace transform of this discontinuous function. Again, you notice one of the nice things about Laplace transforms is that it transforms a function that has discontinuities into a function that doesn't have any discontinuities. And that's actually going to be even more dramatically demonstrated in example 5. So here we have a function that actually has 3 different Heaviside functions in it. So we're going to have to split up our function into 4 different pieces because it's got 3 different discontinuities. We're going to have to sketch the function and again find the Laplace transform. Now, one of the things that we're going to need to do when we do that is use the second shifting theorem. So let's come back to that when we're ready. The first step is to calculate what this function would look like expressed as a piecewise continuous function. So let me just repeat what the function is first. We've got 6t u of t minus 3 plus 9t u of t minus 7 minus 15 times u of t minus 12. So we're going to write this now. In terms of the 4 different ranges of values of t. So I'm going to go all the way over here to do that. So clearly we've got something changing at t is equal to 3, t is equal to 7, and t is equal to 12. So that's actually going to tell us what the different ranges of values of t are. So I'm going to have t less than 3, t is greater than or equals to 3 but less than 7, t is greater than or equals to 7 but less than 12, and t greater than or equals to 12. So what happens to this function then for each of these different values of t? Well, for t less than 3, you can see that this will be switched off, this will be switched off, and this will be switched off. So I'm going to have a big fat 0. Between 3 and 7, these two still remain switched off, but now I'm finally switching on this one, so I get 6t. Between 7 and 12, I haven't yet switched on this guy, because he only turns on after t is equal to 12, but these one have been both switched on, so I'm going to get 6t plus 9t. I'll get 15t. And finally, for t is greater than or equals to 12, all 3 of my Heavisides are now switched on. And so I'm going to have 6t plus 9t minus 15, which is equal to 15t minus 15. So that's my function expressed as a series of piecewise continuous functions. And now I'm ready to sketch what this thing is going to look like. Give myself a little bit of space here. So I've got changes at t is equal to 3, 7, and 12. So there's 3, there's 7, and there's 12. So we know that this function grows like it's 0 first of all. We're including the point on the left, we're not including that point. And then it grows like 6t. So since we're starting off at the value 3, it's going to grow, let's say, something like this. That's 6t. We're including this point, but not including this point. And again, I'm guided by that from the definition of our function. So I'm including the point at 6t for 3, but not including it at 7. Next piece. It grows like 15t. So again, that's going to it's going to be discontinuous, so it's going to grow something like that. And I'm including this point, but not including this point. And this is 15t. And finally, we have 15t minus 1. So that's going to be slightly below this one and increasing with the same slope. 15t minus 15, excuse me. So that's what our function looks like. Now I need to calculate what the Laplace transform of this thing is going to be. So let's pull out another page. And we're going to make use of the Heaviside function to do this, and the second shifting theorem. plus minus 15u of t minus 12. So let's remind ourselves what the second shifting theorem states. It says that if I have a function that's expressed as a shift by c multiplied by a cut at c, that is a Heaviside, t minus c, then its Laplace transform is going to be equals to e to the minus cs times f of s. Where f of s is the Laplace transform of the unshifted uncut function. That is just f of t. So let's think about this for a second. The first thing we have to do is notice whether or not our function is actually expressed as a shift plus a cut. And if it doesn't, we're going to have to manipulate our function so that it does look like that. Once we've done that, we can use the Heaviside, we can use the second shifting theorem to basically calculate what our Laplace transform of our unshifted uncut function is, and then just multiply that by an exponential. So the second shifting theorem basically says that a shift plus a cut in t world turns into an exponential in s world. It's a little bit different from the first shifting theorem, which says that an exponential in t world turns into a shift in s world. Here we're saying a shift plus a cut in t world turns into an exponential in s world. So the first thing to do is to take a look at our function and actually see if indeed we have it in the form of a shift plus a cut. Well, we certainly have a bunch of cuts here. We've got u of t minus 3, u of t minus 7, u of t minus 12. So these are cuts. But I don't have the corresponding shifts. That is, I don't have my function here in the form of something involving t minus 3. Everywhere where t appears, it should appear in the form t minus 3. So I'm going to have to do that artificially. Let's see how that works. So I'm going to write the function 6t u of t minus 3, which again has a Heaviside, so it has a cut, but it doesn't have the corresponding shift. So what I'm going to do is I'm going to do a little trick. I'm going to subtract 3 and add it right back in again. Obviously those two 3's cancel each other out, so there's no worries there. Now what I can do is I can take the first of those, so 6t minus 3 times u of t minus 3, and I'm left over with a 6 times 3. 6 times 3 is 18. 18 u of t minus 3. Now I actually have expressed my function, which had a cut but no shift, as a function which has a cut and a shift at the same place. So I can actually use my second shifting theorem in this example here. Now you may be saying, what about this little extra bit, this bit I added on artificially to compensate for the minus 3 that I was putting in? It ended up giving me an 18 u of t minus 3. So again, I've got a cut, but I don't have a shift. Why? Now, what do I do with that? Well, the answer is that this is a constant. It doesn't depend upon t. 18 has no dependence on t, so it doesn't care about a shift. You can think about this, in fact, as I can shift t to t minus 3, and it's not going to change 18. So this piece here doesn't care about that shift. Another way to think about this is that because this is a constant times a Heaviside, then I can use the Laplace transform of just the Heaviside. I don't need to use the second shifting theorem. Let's do the same trick for the second part of my function, which was 9t u of t minus 3. Just move that down a little bit because I'm going to actually calculate the Laplace transform of those pieces one by one. So this is equals to, again, same trick. Notice it was a t minus 7. Yeah. So same trick. You notice that we've got a shift here, a cut but no shift. So I'm going to artificially stick that shift in by subtracting 7 and adding 7. My cut happens at 7. My Heaviside function is u of t minus 7. So I need to artificially stick in a shift of 7. So I'm going to write this again as u of t minus 7, 9 times t minus 7, u of t minus 7, plus 9 times 7 u of t minus 7. And again, I get something now that's expressed as a cut and a shift at the same place, and a constant times a Heaviside, so I can find its Laplace transform. Now I have the last piece. 15, or minus 15, u of t minus 12. So how do I deal with this one? So again, notice here I've got a cut but no shift. But again, notice that the function here is actually just a constant. It doesn't depend upon t. So it doesn't care about the shift. The Laplace transform of this thing is just going to be given by the Laplace transform of a Heaviside function. Okay, now that we have all our pieces here, we're ready to calculate the Laplace transform of this thing. So let's take our first piece right here. We've got the Laplace transform of 6t u of t minus 3, and that's equal to all this stuff here. So let's start off with that. So we have the Laplace transform of 6t u of t minus 3, and we've seen that that's equals to Laplace transform of 6t minus 3 u of t minus 3 plus Laplace transform of 18 u of t minus 3. So in order to calculate this Laplace transform here, we're going to have to take a look at the second shifting theorem again. So let's just remind ourselves about that. Second shifting theorem says that when I have a shift plus a cut, then its Laplace transform is going to be e to the minus cs times the Laplace transform of the unshifted uncut function. So what we're going to have to do is that we're going to have to remove the cut by getting rid of the Heaviside, and we're going to have to take away the shift. So let's see what that would be in this case. So the second shifting theorem says that this will be e to the minus shift times s, the shift is 3, times the Laplace transform of the unshifted uncut function. So what exactly is that? Well, that's going to be removing the cut, so get rid of the Heaviside, remove the shift, so get rid of that minus 3. So that leaves me with just 6t. I also have 18 times the Laplace transform of the Heaviside u of t minus 3. So this is all going to be equals to e to the minus 3s times the Laplace transform of 6t, which is 6 over s squared, plus 18 times the Laplace transform of u of t minus 3, that's one of our tabled Laplace transforms, that'll be e to the minus 3s over s. Let's apply the same technique to the second piece of our puzzle. We've got Laplace transform of 9t u of t minus 7. We saw that this was the Laplace transform of two pieces. 9 times t minus 7, so a shift plus a cut, plus 63 u of t minus 7. So that was the bit that was left over. Okay, so now what's the Laplace transform of this first thing? Again, I'm going to use the second shifting theorem. It's going to be e to the minus shift times s, the shift was 7, times the Laplace transform of the unshifted, uncut function, which is going to be, getting rid of the cut is get rid of the Heaviside, get rid of the shift means get rid of the minus 7. So that leaves me with 9t. Plus we can take out that 63 to get the Laplace transform of u of t minus 7. Okay, so now I can do this. It's e to the minus 7s times the Laplace transform of 9t is 9 over s squared, plus 63 times the Laplace transform of the Heaviside, which will be e to the minus 7s over s. Last piece, almost there. We've got the Laplace transform of minus 15 u of t minus 12. So that's actually just minus 15 times the Laplace transform of the Heaviside, so it'll be minus 15 e to the minus 12s all over s. So the Laplace transform of our full function then is given by putting all these pieces together. Yes, that's the function f of t. Is going to be 6 e to the minus 3s over s squared plus 18 e to the minus 3s over s plus 9 e to the minus 7s over s squared plus 63 e to the minus 7s over s plus minus 15 e to the minus 12s all over s. So you can see that we turned this function, which had 3 different discontinuities into a continuous function in the Laplace transform world. Now there is actually another way to approach this problem. I won't go through it, but I will show you how you can do it. Let's take a look at our function again. And you notice that our function is written as 6t times a function, t times a function. You might remember from, or you might have noticed from the Laplace transform tables that there is actually an entry for a function of t that looks like that. So for example, if I've got t times a function of t, its Laplace transform would be minus the derivative with respect to s of the Laplace transform of f of t. So I could actually try to solve this particular problem in a different way using this fact that the Laplace transform of t times f of t is equal to minus the derivative with respect to s of big F of s, where big F of s is the Laplace transform of the function without that factor of a t in front of it. So looking at this piece here, for example, I've got 6t u of t minus 3. I could turn that into the derivative, or minus the derivative with respect to s, of the Laplace transform of 6 times u of t minus 3. So that will involve a whole bunch of terms as well, and it will give you exactly the same answer. Okay, let's take a look at another example. We're going to use the second shifting theorem to calculate the inverse Laplace transform of the function e to the minus 3s over s squared plus 1. We're going to do that by identifying that this is a function that is multiplied by an exponential in s world. So that suggests to me that this is actually going to give me a shifted and cut function in t world by the second shifting theorem. So I've noticed that this e to the minus 3s over s squared plus 1 looks like e to the minus 3s times a function f of s, where f of s is equal to 1 over s squared plus 1. So that means that the inverse Laplace transform of this function is going to be a shift and a cut of the function f of t. So f of t is going to be given by the inverse Laplace transform of 1 over s squared plus 1. So that's just sine of t. So what's the shifted cut version of that? It's going to be shift by 3 and a cut at 3. So it's a shifted cut version of sine of t. So what would that look like? Well, it's going to look like the sine function, but starting at t is equal to 3. So this thing is going to be 0 up until 3, and then it's going to oscillate back and forth between minus 1 and 1, just like good old-fashioned sine, except it's been shifted over by 3 units. Okay, let's take a look at example 7. This is an interesting example because it actually is a Laplace transform that we could calculate using either of the shifting theorems. So I'm going to do it both ways. First of all, I'm going to do it using the second shifting theorem, and then I'll try it again using the first shifting theorem. Answer is going to be the same in each case, of course. So we're looking for the Laplace transform of e to the 7t u of t minus 4. And we notice here that this is actually a function that has a cut in it at t is equal to 4, but it doesn't have a corresponding shift in it. So we're going to have to use our trick of rewriting my function so that it actually does have that shift. So I'm going to write this as 7t minus 4 plus 4. Add and subtract that 4. And I've got u of t minus 4. So this thing will be equals to, so what are we going to get? We're going to get 7t minus 4 plus 7 times 4. And I'm going to use the fact that e to the a plus b is equal to ea eb. So the laws of powers there are exponentials. So that will give me the Laplace transform of e to the 28. That's 7 times 4, e to the 7t minus 4, u of t minus 4. So now I can use the second shifting theorem. Let's pull out that constant e to the 28, don't care about that. You can see that this is clearly in the form of a cut and a shift. So it's a cut at 4 and it's a shift by 4. So what I'm going to do is I'm going to use the second shifting theorem to pull that shift and cut out, e to the minus shift times s, and that's going to be multiplied by the Laplace transform of the unshifted uncut function. So what is that? Let's get rid of the cut, get rid of the Heaviside, get rid of the shift, so I've got e to the 7t. So I need the Laplace transform of e to the 7t. It's going to be given by one over s minus 7. That's one of the tabled Laplace transforms. I can actually tidy this up a little bit by putting back together those exponentials, e to the 28 minus 4s, or if I take out a common factor of minus 4, I get e to the minus 4 s minus 7 all over s minus 7. Okay, now let's see the same function, try and find its Laplace transform, but now use the first shifting theorem. So here's the first shifting theorem. And this relies on noticing that the function is multiplied by e to the minus at in front. So we've got the Laplace transform of e to the minus 7t, u of t minus 4. So this is going to be equals to f of s plus we can see that a here is clearly going to be equals to, so that's e to the 7t. There we go. So we can see that a is going to be equals to minus 7. So this is going to be f of s minus 7. So what is f of s? Well, f of s is going to be the Laplace transform of the function without that exponential in front. It's going to be u of t minus 4. Again, that's one of our tabled Laplace transforms, so that will be e to the minus 4s all over s. So what is f of s minus 7? Everywhere I see s, I need to replace it with s minus 7. And you can see that this gives us exactly the same expression in both cases. So we used either of the first or second shifting theorem to find the Laplace transform of this function. Next example is going to get even crazier. We need to use both the first and second shifting theorems, and we can use them in either order. We're getting lots of practice here with Laplace transforms and first and second shifting theorems. So I'm going to just do it one way, and then I'll leave it to you to try and find how to do the calculation in the other order. But we're going to use both of our first and second shifting theorems. So maybe the best thing to do would be to start with the second shifting theorem, because this thing looks like an exponential times a function of s. So this looks like inverse Laplace transform of e to the minus 2s times f of s. So by the second shifting theorem, this will be f of t minus 2, u of t minus 2. So we're using the second shifting theorem here. So what is f here, f of t? F of t will be the inverse Laplace transform of the function without that exponential in front. So it'll be the inverse Laplace transform of 1 over s minus 7 to the power of 4. This is where the first shifting theorem comes in, because we notice that this looks exactly like a simple function of s that's been shifted. So let's write this as the inverse Laplace transform of, let's introduce a new function, big G of s minus 7, where G is the unshifted function. So that would be 1 over s to the power of 4. So by the first shifting theorem, this thing is going to be equals to e to the minus shift t times the inverse Laplace transform of the unshifted function. So that's using the first shifting theorem. Okay. So we have e to the 7t times the inverse Laplace transform of 1 over s to the power of 4. Well, that's going to be t to the power of 3 over 3 factorial. So what we found here is that my function f of t is equal to e to the 7t t cubed over 3 factorial. And my inverse Laplace transform of my original function, e to the minus 2s over s minus 7 all to the power of 4, is going to be a shifted cut version of that. So it'll be everywhere I see t, replace it with t minus 2. And that's all going to be multiplied by a cut at t is equal to 2. So that's how to solve that problem using first the second shifting theorem and then using the first shifting theorem. We needed to use both of them in this case. And again, you could actually do this the other way around. You could use the first shifting theorem first to get rid of this shift. And to do that, of course, you're going to have to rewrite this function so it looks like it's actually got a shift in s up in this exponential as well. You can use the first shifting theorem to deal with that, and then you're going to have to use the second shifting theorem after that. Okay, so now we're left with example 9. Now, example 9 is a challenge problem. So what I'll do is I will leave this problem for you to try yourself. It's definitely a tough one, and we'll discuss it on the online forum.